Hello, this is a presentation on Karl's correlation coefficient by me, Hardik, Shrivastava, and Mohsin Chougale for the subject Foundations of Signal Processing. Next slide. So, who developed Karl's correlation coefficient? Auguste Bevis published a paper in the year 1844 discussing the concept of correlation and defining the correlation coefficient. The statistical idea of correlation was created by Sir Francis Galton in the year 1880. The idea was further developed by Karl Pearson and hence the name Karl's correlation coefficient, also referred to as the Pearson's correlation coefficient. Now, what is correlation and what is Karl's correlation coefficient? So, correlation basically measures the degree to which the two variables move in relation to each other. It measures the association between any two variables x and y, but it does not tell us whether x is caused by y or x causes y, or if the association itself is caused by any third factor. So in this respect, we can define Karl Pearson's coefficient of correlation as a linear correlation coefficient that falls in the value range of -1 to +1, both inclusive, wherein a value of -1 would signify a strong negative correlation, while +1 would indicate a strong positive correlation. Now, what is positive correlation? It basically means change in one quantity is directly proportional to the change in other quantity. In other words, if a quantity x increases, then it would lead to a corresponding increase in quantity y, and vice versa. Similarly, we can define negative correlation wherein a change in one quantity is inversely proportional to the change in other quantity. So in this case, when quantity x increases, it would lead to a corresponding decrease in quantity y, and the decrease in quantity x would lead to an increase in quantity y. So here we have zero correlation. Zero correlation basically means change in one quantity is completely independent of change in other quantity. Now, because Karl's correlation coefficient is a linear coefficient, we can see that a value of 0 signifies that there is no linear relationship. The variables might have a non-linear relationship among themselves. Karl's correlation coefficient is usually represented by the letter R, and the formula can be seen on the right hand side. The range for this value for R is between 1 and -1, both inclusive, wherein a value closer to 1 would indicate a positive correlation, value closer to -1 would indicate a negative correlation, and any value closer to 0 would indicate 0 or no linear correlation.
Thank you, Hardik.
Thank you.
I'll take over. This is Mohsin Chougale. Let's go over the steps to calculate Karl's correlation coefficient. The first step, if we are given two signals x and y, we need to calculate the mean values of those points. Next, we'll need to calculate the standard deviations of the values of x and y from the mean value. Third, we'll need to square these deviations. Next, we'll need to calculate the product of the square of the deviations of x series with the square of deviations of the y series. And lastly, we'll calculate the Karl's correlation coefficient by plugging in the values given in the above formula. Now, we have implemented this particular calculation in a Python program and we have used the math module. Let us go over how the function has been defined. Here, x and y denote the two signals. Sum of x denotes sum of x, sum of y denotes sum of y. And then if we go down in this while loop, we are calculating sum of xy and the square sum of x as well as the square sum of y. And lastly, here we calculate the correlation coefficient using the formula given above. Now, let us look over the few cases as outputs that we get. The first is the perfect positive correlation. If you notice two signals x and y, they both are strictly increasing. Thus, they show a very high correlation coefficient, around 0.993. Next, we have a moderate positive correlation. Now, in this, if you notice, the first signal increases in value, then decreases, whereas the second signal decreases first, then suddenly increases, and then decreases. So, it is showing similarity only in the second half of the signal, and thus it is showing a moderate positive correlation of 0.46. Next, what we have is the perfect negative correlation. What does this mean? This means that in this case, x signal is strictly increasing, whereas y signal is the reversed signal of x, so it is strictly decreasing, thus showing that it is completely inversely related. Thus, Karl's coefficient comes out to be -1. And last but not the least, we have the near zero correlation. Now, in the first signal, x of n is strictly increasing 1, 5, 10, 15, 20, whereas the second signal is oscillating between values 2 and 1. Thus, there is no particular correlation, or these two signals aren't linearly dependent on one another. Thus, we can notice that they have a very low Karl's correlation coefficient, which comes out to be 0.02, nearly equal to 0. These are the references that we used for understanding the theory behind Karl's coefficient and implementing the algorithm, as well as writing down the Python code for the calculation. Hope you understood what Karl's coefficient is.